Okay, so we're going to start chapter 3, which is all about polynomials, and later we'll do at least some part on rational functions. But for now, we're going to focus on what are called polynomials. So first, let's just define what is a polynomial. So a polynomial is a function, we'll call it p of x for polynomial, where p of x is equal to a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus so on and so forth plus a1x plus a0, where, so what are these? We have some notational things going on here. So a sub 0, a sub 1, a sub 2, all the way up to a sub n are real numbers, and a sub n is not 0. So these little subscripts, so these guys right here, those are called indices, or indices. So we'll say the index of a sub n is n, and here n is a positive, n is a, well, I'll just say a non-negative integer, non-negative integer. Okay, this is a symbolic notation. And here we also say, we say that the degree of p of x is n, meaning it's the highest power of x that is there in this polynomial. So because, and this is because the highest power of x is n in this polynomial. Okay, so let me just give an example here. So example, let's say p of x is 4x cubed plus 2x squared minus 1. So what would our a sub 0, a sub 1, be? Well, first let me just rewrite this as 4x cubed plus 2x squared plus 0x. Notice there's no x term, so I can write in 0x and then minus 1. So here, a sub 0 would correspond to this number, this constant term right here, negative 1. Let me do this with a different color so we can distinguish a little bit. So a sub 0 is negative 1. A sub 1 is 0. A sub 2 is 2. A sub 3 is 4. So let me write these down separately. And the degree of this polynomial, the degree, we say the degree for shorthand DEG and then parentheses p of x, this is equal to 3 because 3 is the highest power of x that occurs. Okay. So for this section, what we're going to do is we're going to restrict our attention. So we're going to restrict attention to what are called quadratic polynomials. We can say quadratic functions. So what is a quadratic polynomial? Let's define that as well. A quadratic polynomial is one of the form so it's p of x is equal to ax squared plus bx plus c. So you probably would have seen this in some previous algebra course. And well, it's going to turn out, and we'll see how a little bit later, but it's going to turn out that every quadratic polynomial can be put into what's called vertex form. So what is the vertex form? Well, vertex form, where the vertex form is p of x is equal to a times x minus h squared plus some number k. And this a right here is the same as this a right here. So how do you convert from one to the other? I'm going to save that for the next video. For now, we're going to assume that we have a polynomial already in vertex form and then do everything that we want. And then in the next video, we'll show, using completing the square, how to go from a general quadratic. So eventually we'll want to go from here to here. And the method will be completing the square. So the method will be completing the square. But for now, again, we're going to assume that we already have this. So let's do some examples with quadratic polynomials that are already in vertex form. So let's start with the following example. I guess let me use p of x since I've been using p of x. Okay, so first off, what do we want to do here? So we want to do several things. So we want to find what's called the vertex, and I'll tell you what that is in just a second. We want to find the x and y intercepts. We want to find the domain and range. And we want to find any what are called minimum or maximum values of p of x. So first off, let's just do this without really, if we don't, there's kind of a short way to do this, but let's just plug in points to start off by getting the graph. Oh, I forgot to mention that. We want to find the graph as well. Okay, so let's actually start off with the graph, and that'll kind of help us see everything. And let's just do this for this round by plugging in some points. And what I'm going to plug in is I'm going to plug in 0, I'm going to plug in 1, I'm going to plug in 2. That's actually good enough. So if I plug in 0, I get 2 times negative 1 squared plus 3, which is 2 plus 3, which is 5. Here I get 2 times 0 squared plus 3, which is 3. Here I get 2 times positive 1 squared plus 3, which is 5. And so what ends up happening is we have 0 and then 5 somewhere here, 3 somewhere here. So we have a point there. And then at 1, we have the point here at 3. And then at 2, we have the point back here at 5. So we're going to get this kind of parabolic shape. So all of these graphs are going to be parabolas. And hopefully you can just think of y equals x squared is like your basic parabola. How do we get to this? Well, essentially, so you can think of it like this. How do we get this graph without doing all of this? Well, first off, notice that this base point right here, this is the point 1, comma 3. And this is actually the vertex of the graph. It's the base. Think of it as the base of the parabola. How do you get to that base? Well, think of it like this way. Suppose we started with 2x squared, right? If we started with just y equals 2x squared, then that would just be a graph like this, right? Because it's just a multiple of x squared. It just stretches it a little bit. You still have the base point here is 0, 0. Then if you replace x with x minus 1, this is a shift 1 unit to the right, because we replaced x with x minus 1, and then we added 3, and that shifts up. That's a vertical shift up by 3. And so the base point 0, 0, this also then, the base point shifts to 1, 0, meaning I shifted 1 to the right, so my next parabola here would look like just the same thing except based in 1, 0. And then I go up by 3. So 1, 3 to get my final graph here. Okay. So the point is that this numbers 1 here and 3 are very important because they are actually the vertex. So notice in the general form of a vertex form, we have ax minus h squared plus k. So it turns out that the vertex is actually just h comma k. For example, in our case, we had 2x minus 1 squared plus 3. So h was actually positive 1, k was 3, and that's exactly the vertex in this case. And once you have a vertex, all you need to know is this number 2, is it a positive 2 or a negative 2? So note that this is a is positive, or a term here is positive, which means we have a parabola opening upward. And that's sort of the quick way. Once you have something in vertex form, then all you need to know is the sign of this a. If it's positive, we're going to have an upward pointing parabola. If it's negative, we're going to have a downward pointing parabola. Okay? So what we're going to do is we're also now going to find the x and y intercepts. So what we need to do now, so let's find the x and y intercepts. So how do we find an x and y intercept? Well, remember that an x-intercept is found by setting the y equal to 0. So the y value being 0 is the same as having 2 and then x minus 1 squared, plus 3. So, well, what do we have here? We have x minus 1 squared, or 2 times x minus 1 squared being negative 3. X minus 1 squared then is negative 3 halves. And now, well, we'll see this geometrically, but algebraically now, that would mean that x minus 1 is plus or minus the square root of negative 3/2. Well, but the problem is now we have a square root of a negative number. Square root of a negative number. And so that's not, we can't do that, right? That's no longer a real number. So what that means is there are actually no x-intercepts here. So notice in the final graph right here, this graph never crosses the x-axis. So notice this never crosses the x-axis. So either you could see that geometrically, but algebraically, we can see that if we had to solve, we would get the square root of a negative number. So hence there's no x-intercepts. So let's look at the y-intercepts. Y-intercepts. How would we find a y-intercept? Well, p of x, let's start with the original equation, x minus 1 squared plus 3. For a y-intercept, we set x to be equal to 0. So we have p of 0, that's 2 times negative 1 squared plus 3, and that's 5. So our y-intercept is actually the value 0, 5. Okay, so we found our intercepts, we found our graph, we found our vertex. We next want to find the domain and the range of this function of p of x. So the nice thing about the domains for these problems, for polynomials, and I'll just state this as a general statement, the domain of any polynomial, to be quadratic, it could be third degree, it could be any degree, the domain of any polynomial is all real numbers. And the reason why is because you're just multiplying numbers. You can multiply any number you like. So the domain in this case of p of x is everything, negative infinity to positive infinity. Okay. What about the range? Well, let's look back at the graph. The range, remember, is the set of y values that come out when you plug in all of the x values. So what do you have here? You have a graph starting here at base point 1, 3, and you have a parabola pointing upward. And so what happens here? Notice that the smallest y value is 3, right? All the other values are above this vertex y value. So notice this is actually our k value. So this actually, before we jump into the range, I guess it's a good thing to say, this is actually what's called the minimum value of p of x, because it's the smallest y value you can get. So this is essentially the y value at the vertex. That actually is the minimum value, because it's the smallest y value. That's what we mean by minimum value. And then it just goes up from there, right? So the y values that occur are, well, they're at least 3, but then you get every single y value above that. So the range actually ends up being 3 to infinity. So we found our range, we found our domain, we found our minimum value. The question is now, is there, the last thing that's there is there a maximum value of p of x? Now, what is a maximum value in general? I haven't really talked about it. I'm just kind of using this as a very intuition. So before I jump into that, let me just sort of mention in general. Suppose you had a function like this. Okay? Pretty much a maximum value this value is the y value at the top of a hill. So if you had the top of a hill right here, suppose this was like 1 and this was 4. So this point, this number 4 here would be a maximum value. It's actually called a local maximum value, but that doesn't matter. Something that's at the bottom of a hill right here, say this is the point 3, and this is the value -2. So this is the point 3, -2. This -2 would be a minimum value. Okay, because kind of you can think of, if I'm around this region, this is the smallest I can get. If I'm around this region, this is the highest I can get. So the question is there a maximum value for this function? And since this just keeps growing and growing, there's no maximum value. Because it just keeps growing and growing. No matter what value you can think of, you still get more than that. So there are no maximum values, but there is this minimum value of 3. That we attain that value at x equals 1. Okay, so to summarize, let me just summarize everything here, because that was a little bit little winded. To summarize everything, the vertex here is 1, 3. And because a is positive here, this value is positive, we have a parabola opening up from the vertex, opening upward. Not only that, we have no x-intercept. The y-intercept corresponded to the point 0, 3. The domain was all real numbers. The range was everything above 3. And we had a minimum value of 3, which occurs at x equals 1. And this is pretty much corresponding to the vertex point. Okay, so this was everything that we wanted to know about this function. And what I'm going to do is I'm going to leave you with an exercise here to do the same thing except for a downward pointing graph. So g of x is equal to -3x plus 1 squared plus 4. And so here the main difference is, so they're going to be two things. This is going to be a downward pointing graph, because we have a negative a value. We'll have both x and y intercepts. And this thing will have a max value, but no minimum. So you can try to figure out, and I'm just giving you some hints for if you want to do this on your own, but I'll start the next video with this exercise. Okay, until next time.